In this video, we'll be covering section 5.5, nonlinear systems of equations. So our main objective is to simply solve nonlinear systems. We'll start by solving systems that have real solutions, and then we'll see some examples that have non-real complex solutions as well. And then the last thing that we'll do is look at applied problems with nonlinear systems. So what is a nonlinear system? And we've been solving systems of equations, but in each of those examples, the system, each equation has represented either a line or a plane. And the way we could tell they were linear systems is that the exponents on each of the variable terms were only one, and none of the variables were multiplied together. So that ensured that we had linear systems. But in this section, we're looking at nonlinear systems. So here's two examples of nonlinear systems. The first one is nonlinear because this equation has a square on the variable x. And that immediately means that its graph does not represent a line, it doesn't represent a plane, so it's a nonlinear equation. The second equation in that system is a line, but as soon as you have one equation that does not represent a linear equation, it's a nonlinear system. Second example here, again, this equation would be nonlinear because there are squares on the x and the y. This actually represents the equation of a circle. And then the one below it is nonlinear because we have this absolute value. Now the nice thing is that even though these systems are nonlinear, the methods that we used in previous sections should still work here. So substitution works and elimination works for some cases as well. So let's start by looking at an example with substitution. Okay, so this is a nonlinear system again because we have the square here. With the substitution method, the strategy is the same thing. We simply want to try to isolate one of the variables. So it doesn't really matter which one. I'm going to choose to get y by itself in this equation. So getting y by itself would give me y equals -2 minus x. I can then take this expression and plug it into the equation above, just as we would with a normal linear system. So when I do that, I end up with x squared minus the quantity -2 minus x equals 4. Distributing the negative, I get x squared plus 2 plus x equals 4. And then this is quadratic, so we can use normal methods to solve this. So we're going to move everything to one side and put the powers in descending order. And then we try to factor this expression. If it doesn't factor, we can always go to quadratic formula, but I believe this one factors nicely. We need two numbers that multiply to give us -2 and add to give us +1. So it looks like +2 and -1 give us what we need. So we end up with x is equal to -2 from this factor and x equals +1 from this factor. So then we take each of these, both of them, individually and plug them back into this. So we do want to keep track of, where we're getting each number. So I'm going to write down that, hey, I'm plugging in -2 into this. That gives me y will equal -2 minus a -2, which gives me 0. So this corresponds to an ordered pair. The ordered pair would be the point -2, 0. This is one of our solutions to the system. X is -2, y is 0. Okay, then we do the same thing for the x equals 1. And we get -3 from this one. So this gives us the point of 1, -3. All right, and then we could still represent our solution using set notation. So just list each of the points. And this illustrates one big difference from linear systems and nonlinear systems. With a linear system, you had exactly one solution, or you had infinitely many solutions. You could also have no solutions, but you could never have two distinct solutions, which we do end up with in this example. Now over here, we have a graph of each of the equations. These graphs are not required to do these problems, but they help illustrate what's actually happening. So the blue graph here is the graph of the first equation, which is a quadratic, and then the second equation is the linear equation, and we can see exactly where the two intersect. These intersection points represent the solution to our system, and you can see that's why we end up with two of them, because that line intersects the parabola in two different points. Okay, so just to highlight that a little bit more, if you have a nonlinear system that consists of a line and a parabola, like the previous example, then there are three possibilities here. It might have no solution. It might have exactly one solution, meaning that the line is tangent to the parabola, or it could have two solutions, 2 points of intersection, which we saw in that previous example. Okay, so let's try another example. So in the previous one, we looked at using substitution, but some problems are going to work better if we try to use elimination. Particularly if you have a system of equations where both of the variables are squared, then typically elimination is going to work better. This really kind of models exactly what a linear system would look like, because each of the variable terms match. The only thing that's different is their coefficients. So if we're going to do elimination, this one's set up easily. We can just go ahead and add these two equations down. So we would get 3x squared is equal to 12. So x squared equals 4. Take a square root, and here's where you have to be careful. When we square root it, you need to make sure you do plus or minus. So we get plus or minus 2. Two different x values. So then to find the y values, we just plug them back in. So we have x, plug in, let's do the positive one first. And you can plug it into either equation, so might as well do the top equation. It's going to be the easiest. So that would say 4 plus y squared equals 4, which would say y squared is equal to 0. Take a square root, so y equals 0. Technically plus or minus 0, but plus or minus 0 is still 0. All right, so that gives us one solution, the point 2, 0. Okay, then do the same thing for negative 2. And hopefully you can see that if you plug negative 2 into this, you're going to get the same thing. It happens a lot with these, but not always. So do take the time to actually closely look at it and see if, plugging in the negative will actually result in the same thing. So I'm going to skip the steps there. If you do all of that, you still get y equals 0. So that gives us the solution of negative 2, 0. And that's it. Those are our solutions for this system. On the right side, I graphed the solution, or graphed the equations. But in order to make this happen, your calculator can't readily graph an equation like this. So in order to graph it, what I did is I solved it for y. So I moved the x squared to the other side, and then I took a square root. But when we take that square root, we do have to put in plus or minus. So it actually consists of two graphs. In y1, I put the positive one. In y2, I put the negative one. And so what those corresponded to is this upper semicircle and the lower semicircle. So in order to graph that single equation, I had to enter it as two separate functions. As you can see, this graph represents the equation of a circle of radius 2. I did the same type of thing for the bottom one. The graph of this is called a hyperbola. It's a type of conic section. And again, I got two different equations, one with a plus in front of it, one with a minus. So the positive one is the black curve that you see here, and then the pink one would have been the negative. Now, it looks like these aren't touching at all, but that's just because your calculator doesn't have the best resolution. It can't keep filling in these dots, but this graph really does connect right here and over here, and it intersects that circle exactly at those points there, exactly at these 2 points. So those are the solutions to that nonlinear system. Okay, so let's look at a messier one. So the next example is messier because we've got square terms, but we also have the product of x and y in it as well. So we're going to use a combination of elimination and substitution to solve this. Now again, you don't need the graphs, but just to highlight what's going to happen here, the top equation that you see here is this ellipse, or sorry, backwards, I got that backwards. The top equation is the hyperbola, the red one, and then the bottom equation is the ellipse that you see here. And so the solutions are where these things intersect. And you can see that we actually are going to end up with 4 different solutions on this. Okay, so the first thing I notice here is if we just go ahead and subtract these 2 equations, then we can eliminate all the square terms. The x squareds are going to drop out, the y squared is going to drop out, and what we end up with is just 4xy equals 16 when we subtract down. So then I'm going to go ahead and solve this for y. You could solve it for x or y, it doesn't make a difference. I'm just choosing to solve it for y. So to do that, I'm going to divide the 4x over. So y equals 16 over 4x, but that reduces. We get y equals 4 over x. So then what I can do is I can take that expression and plug it into the y's in one of the equations. So I'm going to take this expression and I'm going to use the bottom one. I'm going to plug it in for this y and for this y here. Okay, so if I do that, we will get x squared minus x times 4 over x plus 4 over x squared equals 6. Okay, so then we simplify this. X's here cancel, and then we can square the top and the bottom of that fraction. So we get x squared minus 4 plus 16 over x squared is equal to 6. Okay, so now we don't really want the fractions the way that we have them. So the best thing for us to do would be to multiply everything by x squared. So if we do that, then you're going to get x to the 4th minus 4x squared plus 16 equals 6x squared. So again, I just multiplied all the terms that you see here by x squared. That cancels the fraction that you see here. Okay, so then you might notice that this is what we would say quadratic in form. It's quadratic in x squared. So I'm going to move everything to one side and maybe that'll become more clear. We did these back closer to the beginning of the year. It looks just like a quadratic equation, except this is a 4th power and that's squared. So to show you a little bit more closely what I mean, I could write the first term as x squared squared minus 10 times x squared plus 16. So what we can do is we can say, let's let u equal x squared. And we can put u in place of this. So that would then become u squared minus 10u plus 16 equals 0. And then we just try to solve this like a normal quadratic. Alright, so we're looking for 2 numbers that multiply to give us 16 and add to give us negative 10. So it looks like a minus 8 and a minus 2 will work for us. So this gives us that u equals 8 and u is equal to 2. But we can't stop there because we weren't looking for u, we were looking for x. So we plug x squared back in. And then we can take a square root. But again, we have to put in that plus or minus. Okay, this radical can be simplified, so that gives us x equals plus or minus 2 square root of 2. And that one just stays the way that it is. So now we have 4 different values that we have to plug back in. You can plug them back into any equation. You could plug it back into the first 2, but those are pretty messy. So the best place to plug them in will be to take these and just simply put them into this. We'll do that with both of them. And this is where we're going to end up with our 4 solutions. We have 2 x's here and 2 x's here. Those all have to be plugged back into this. Okay, so to do that, I'm going to clear the page and just to make the pen not lag so much. So I'll be right back. Okay, so I've cleared out most of the page, kept our x solutions that we found, and this is the equation we're going to substitute back into. So let's bring the pen back up. Okay, so we're going to plug in 2 square root of 2 first, so we will get y equals 4 over 2 square root of 2. And we can cancel right here, so this is really just 2 over the square root of 2. But we don't want to leave it like that, so we need to rationalize. To rationalize the denominator, we simply multiply the numerator and denominator by the square root of 2, and that gives us 2 square root of 2 over 2. Square root of 2 times square root of 2 is just 2. But then we can see those cancel, so we just get square root of 2. So this gives us our first solution, which is 2 square root of 2, and then square root of 2 for the y. So then we would go back, and we would need to do the same thing with the negative of that, so negative 2 square root of 2. But you can see with this equation, when I put in the negative to this, all the algebra is going to be the same. The only thing that's going to be different is we're going to get a negative value there. So y is just going to come out to negative square root of 2. Alright, still getting slow down here. Okay, so that gives us our second solution of negative 2 square root of 2 so second solution is negative 2 square root of 2 and negative square root of 2. Okay, so then we still have to go back and do the same thing with plus and minus 2. So x equals 2. So when it's going to be cleaner, just plug 2 into this. You can see you get y is equal to 2. And if you put in negative 2, we get out y equals negative 2. So our final two solutions is 2, 2, and negative 2, negative 2. So we have 4 total solutions for this nonlinear system, corresponding to these 4 points that you see here. Okay, so the next example we want to look at is different from the previous because it has an absolute value in it. We're going to do the same types of techniques. We're going to do substitution again. And you can technically solve for either the absolute value or for the y, but I typically recommend that you isolate the absolute value. Whichever variable has the absolute value on it, that's usually the best one to get by itself. Just makes the algebra a little bit easier than the other method. So this will tell us that absolute value of x equals 4 minus y, just subtracting y on both sides of that. Now the important thing here to recognize is if I take an absolute value and I square it, that is the same thing as just x squared. So squaring this is the same as x squared, which according to this would be the same as 4 minus y squared. So in place of x squared up above, you can actually put this expression in for that term. So making that substitution gives us 4 minus y squared squared plus y squared equals 16. Now we have a single equation with one variable, so we can solve this. This will end up being quadratic again. So we have to FOIL here. This becomes 16 minus 8y plus y squared, just foiling this. And then the second y squared is from this term. So then we just need to combine like terms and move everything to one side. So the y squareds combine to give us 2y squared. We still have minus 8y, and then the 16s actually cancel on this. So this becomes a nice, easy quadratic to solve. All we have to do is take a GCF out. So factor out a 2y. 2y divides evenly into both terms. And then from this we get y equals 0 and y equals 4. So then we just take those and plug them back in. So we'll start with the y equals 0. So I'm going to plug it into the bottom equation. You can technically do either one, but let's just show it in the bottom one. Alright, so since the 0 doesn't really matter, that really says absolute value of x equals 4. So remember, absolute value is distance from 0. So we're saying that x is 4 units away from 0, which means x could be in two different places. X could be at plus or minus 4. So the important thing here is this actually gave us 2 points. We started with 0, but we got 2 different x values for it. So we have 2 solutions from this, 0, 4, and 0, negative 4. Okay, now let's go back and put the y equal 4 in. So this would be absolute value of x plus 4 equals 4. Subtract the 4 over and they cancel. So you just get absolute value of x is 0. And so this says the distance x is from 0 is 0. Well, there's only one solution for that. X would have to be 0. So this gives us the point of... oh, I had these backwards. So y is 0. These should be reversed. So let's go back and change that. So this actually should have been 4, 0 and negative 4, 0. And then this one is the 0, 4. Alright, so those are the 3 solutions for this system. And you can see I've graphed them over here on the calculator. So again, the top equation had to be graphed as 2 separate functions. And the bottom equation gives you this absolute value graph that you see here. And you can see in the picture there are 3 points of intersection. Really, there is no gap here. The calculator just doesn't have a good enough ability to draw that. Those are the 3 solutions that you see here. Negative 4, 0, 0, 4, and 4, 0. Okay, the next example doesn't really look different from the previous ones that we've done. We've got just squared terms, so this doesn't look any different, but if we look at their graphs, we will see how it is different. So the top equation is the equation of a circle with a radius of square root of 5. That blue circle is this equation. The second equation is an equation of an ellipse, and what we can see from this graph is they don't intersect at all. Now, what that tells us is that it has no real solutions, but that doesn't mean it has no solutions at all. It still can have complex solutions. In this case, they will be non-real complex solutions. But we don't need to know that ahead of time. You just solve it like you would any of the other ones. So I would use elimination. I'm going to multiply the top equation by negative 4. So we get negative 4x squared minus 4y squared equals negative 20. And then the bottom equation stays the same. Add down, we end up with negative y squared equals negative 9. Divide by the negative, y squared equals 9. So y is going to equal plus or minus 3. Okay, so then take this and plug it back into either equation. So I'm going to start with the positive, and I'm going to plug it into the top. So that's x squared plus 9 equals 5. Subtract the 9 over, and you get x equals negative 4. Oops, sorry, x squared is negative 4. Take the square root, we get x equals plus or minus, because we're taking a square root of a square here, the square root of negative 4. Now we've learned when you take a square root of a negative, that is where we get the imaginary constant, and the square root of 4 is also 2, so this is really just plus or minus 2i. Okay, so that gives us 2 different points, 2 different solutions for this. We have plus, or so let's just do 2i, and then 3, right? The y value is 3 for each of these, and then negative 2i with 3. So these are our first 2 solutions. If we go back and do the same thing for negative 3, when I plug it in, I will get the same equation. X squared plus 9 equals 5, because the negative gets wiped out with that square. So I don't need to do all this algebra again, I know the x is going to come out to the same thing, plus or minus 2i. So our last solution's going to be the same as this, just with a negative 3 there. So 2i with negative 3, and then a negative 2i with a negative 3. So these are the 4 solutions to this system. They're all combinations of non-real complex. At least one coordinate is non-real complex, which is why we don't see an intersection here. But they still represent solutions to that system. In our last example, we want to look at an application problem involving nonlinear systems. So let's read the problem. It says a box with an open top has a square base and 4 sides of equal height. The volume of this box is given to be 75 cubic inches and the surface area is 85 square inches. From that information, we want to find the dimensions of the box. So we've made a model of the box over here. The base, as it says, is square, so we're putting dimensions of x and x on the base, and then the height is labeled with y. So let's start with volume. We know that a volume for a box is length times width times height. And in this example, length and width are both x, so that is x times x, and then the height is y. Now, my notes had a typo on it. I think yours are correct, but I had 74 here, so I had to correct that. That should have been 75, so we can plug that in here. The volume is given to be 75. This could be simplified to 75 equals x squared y. So this is our first equation. It has 2 variables, so in order to be able to solve the problem, we would need a second equation with both variables, and that's where surface area comes in. So to find the surface area, we just need to find the area of all the faces of the box. So if we start with the bottom is a square, so its area should just be x times x. So for surface area, we start with the bottom, x squared. We don't need to worry about the top, remember, because it is an open top box. Okay, so then we just need to add on the area of these lateral surfaces, the lateral faces, the sides of the box, and their dimensions are x and y. There are 4 of them. They're all the same. So we know that this is 4xy. This is the area of all of the sides. So this expression represents our surface area, and surface area is given to be 85. Oops, forgot my x in there. Alright, so that is, these 2 equations together make up our system. There are lots of techniques that you could use to solve them, but probably the most obvious one would be to solve this first equation for y, get y by itself, and then substitute into this equation. So if we do that, all we would do is divide the x squared over. So we end up with this. All right, then if I substitute that into this y here, what we get is 85 equals x squared plus 4x times 75 over x squared. And then if we simplify this, we can cancel an x here, and we can go ahead and multiply the 4 and the 75. So we need to solve this equation, and we don't like that x is in a denominator. So what we can do to get rid of it is just multiply all the terms by x, which gives us 85x equals x cubed plus 300. This is a polynomial, so to solve it, we should move everything to one side, which would give us x cubed minus 85x plus 300 equals 0. All right, now it'd be nice to factor this, but it's not quadratic. So we're going to need to use a different technique. Since it's cubic, typically to factor a cubic, we would need to have 4 terms, and then we could factor it by grouping. But this only has 3. So we're going to have to go back and try to use the rational root theorem. So if you recall, the rational root theorem says if you have any polynomial, not just a cubic, but any polynomial. And if it has a nice zero, a rational zero, then that zero has to, the numerator of it has to be a divisor of this 300, and the denominator would have to be a divisor of this leading coefficient, which is a 1. So really what that's saying then is, if we have a nice zero, it just has to be a divisor of 300. We would typically start by checking 1 and -1, because they're just the most commonly used, but I can tell you for this problem that neither one of those are a zero. So we're going to test 5 first, and we're going to move to a new screen to do that. So in order to test to see if 5 is a zero, we could just plug it in, but it's going to be more useful to us if we do synthetic division. So remember, here we write down the coefficients of the polynomial. So 1, 0, because there is no squared term, minus 85, and then 300. Okay, so then drop the 1 down, multiply the 5 by the 1, add down again, multiply, add down again, multiply, and we can see it is a 0 because we get a remainder of 0 right here. So that tells me this is a solution to that equation. So we know x equal 5 is a solution. And we can go ahead and find the correct y value now as well. Remember, we solved for y, and we had that y was 75 over x squared. So if I plug that into this gives me y equals 75 over 25, which is 3. So we have one set of dimensions that work. 5 inches, we shouldn't say by, we should just say x. So x is 5 inches, y is 3 inches. So the base has dimensions 5 by 5, and the height was 3. So that is one solution for the problem. But there could be more. So remember that right now we've just factored one factor out of this. The remaining, the depressed polynomial, is sitting here. And that polynomial is x squared plus 5x minus 60 equals 0. It's a quadratic. So we can also solve this for additional solutions. You can try factoring it, but it doesn't factor. So if it doesn't factor, that means we got to go to quadratic formula. So x will be the opposite of b, which is 5 in this case, plus or minus the square root of b squared, which is 25, minus 4 times a is 1, times b, which is negative 60. And all of that is divided by 2 times a, which in this case is 2 times 1. If we simplify this, this is negative 5 plus or minus the square root of, this would be negative 240. Add on the positive 240, because negative times negative is positive. Positive 240 plus the 25 is 265, all over 2. So these are the other possible values for x. However, notice that if we choose the one where these are both negative, x would come out as a negative number. So that's not really okay. So the only one that's going to work is negative 5 plus square root of 265 over 2. And that comes out approximately to 5.639. And then to get the y value that corresponds to that, again, we go back up and plug it in. So y would equal 75 over this number squared. Now really, we shouldn't use the rounded value. If you do use the rounded value, then I think you get 2.359 inches. If you don't use the rounded value, then you get 2.358. So in the book, they actually used the rounded value, so I don't know what MathXL is going to require, but technically either one of those should suffice. So we had the original solution, and then the secondary solution was x is approximately 5.639 inches, and the y value for that one was approximately 2.359 inches. So two different possible solutions where it's a square base and has a volume of 75 and also has the surface area of 85. All right, and that completes this section of notes. Make sure you're emailing me questions if you have them as you proceed through the homework, and we'll see you on the next one.